Okay, we're going to take a quick look at acid-base theory so that we can apply that when we start doing some calculations with buffer solutions. Stuff that you should have learned long ago in Chem 1, but may not have. Little review of acid-base theory here. The Arrhenius definition of an acid and a base. An acid is anything that spits out a proton. H plus is a proton. A hydrogen atom where you've removed the electron is merely a proton. So, typical example of something behaving as an acid, hydrobromic acid can dissociate into bromide ion and a proton. Now, in aqueous solution, you don't really have protons all by themselves. Those protons grab onto a water molecule and they form a so-called hydronium ion, H3O+. So if you look at older textbooks when they're discussing pH, they'll say that the pH of a solution is the negative log of the proton concentration. Modern textbooks will say the pH of a solution is the negative log of the hydronium ion concentration. So again, way back when, we used to just talk about acids as spitting out the proton. Nowadays, we realize the proton hooks onto a water molecule, forming the hydronium ion. Anyway, you got to know your strong acids. There's 6 common strong acids out there. I've listed them here. You have hydrochloric acid, hydrobromic acid, hydroiodic acid, wickedly strong stuff, the hydroiodic, nitric acid, sulfuric acid, which is battery acid. That's the stuff that's in your car battery, sulfuric acid, and perchloric acid. These are all very, very strong acids. They completely ionize in solution. They're really good at taking that proton and sticking it on the water molecule. So those are acids. Bases. The Arrhenius definition of a base is a base releases the hydroxide. We think of the hydroxide as being the opposite of a proton because, hey, guess what? If you got yourself a proton and you put it together with a hydroxide ion, what are you going to make? You're going to make water. So protons, really corrosive things. Protons or hydronium ions in solution will dissolve metals. Hydroxide ions will dissolve aluminum and quite a few other metals. Put them together, what do you got? Water. So, acids, bases, they're opposites of each other. So, bases are things that spit out the hydroxide ion. Now, your common strong bases are the hydroxide salts taken from the first 2 columns in the table: lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide. I imagine rubidium hydroxide, cesium hydroxide are also good strong bases. And these guys are bases. They're ionic compounds where, the metal carries the positive charge. The hydroxide ion, OH, carries the negative. So you take lithium hydroxide, dissolve it in water, boom, spits out hydroxide. Sodium hydroxide, dissolve it in water, it's going to spit out hydroxide. Potassium hydroxide in water will give you K plus 1 and your OH minus 1. So I was just going down the lithium, sodium, potassium. Now, the second column here, your calcium, strontium, barium hydroxide. You get 2 hydroxides per molecule. So calcium hydroxide dissolves in water, calcium ion, and 2 hydroxides. Barium hydroxide gives you the barium plus 2, and of course 2 hydroxide. Strontium, same thing. So those are your nice, strong bases. Now, the Arrhenius definition talks about acids. They spit out protons. Bases, they spit out hydroxides. A more useful definition for acids and bases is the Bronsted-Lowry definition. The Bronsted-Lowry definition doesn't worry about hydroxide ions at all. Instead of having 2 points of reference, and your old definition had 2 different points of reference, the newer definition here, all you're talking about are protons. You forget about hydroxide ions altogether. It's all about the protons. And in every acid-base reaction, there's a transfer of one lousy little proton from one species to another. If you move H plus from one species to another, you've done an acid-base reaction. The acid is the proton donor. The base is the proton acceptor. So the guy that gives up the H plus is the acid. Wherever the H plus ends up, that was the base. Now, why change the definition? This definition lets us see acid-base reactions in a more relative manner. There are a lot of chemical species out there that can react as an acid in one setting. In a different setting, they can react like a base. So an example here is given below. We have a bicarbonate ion here, HCO3 minus 1. You would get that by dissolving baking soda or sodium bicarbonate in water. Sodium bicarbonate or baking soda is that stuff. You dissolve it in water, you get the sodium ion, which we don't care much about, and we also get the bicarbonate ion. So if you have a solution of this, well, this stuff could react as an acid or it could react as a base. Let's look at this first reaction. If you have this stuff and you were to add sodium hydroxide to the solution, hey, these hydroxide ions are going to reach out and remove that proton. That hydrogen there gets pulled off. Notice when that happens, you go from being bicarbonate to carbonate. So bicarbonate, carbonate. The only difference in those two formulas is a difference of one lousy proton. So what you've done is you've transferred a proton. Moved the proton from here to make this. Where'd the proton go? Oh, the proton went on to here. If I add the proton to that, it becomes water. The only difference between these two formulas is the difference of one proton. So in cases like this where two species differ in formula by the presence of one lousy proton, they're conjugate acid-base pairs. We'll talk about that more later. But in terms of our definition, he's giving up the proton, so in this reaction, this guy's acting as an acid. He donated the proton. This guy's acting as the base. He accepted the proton. For what it's worth on the conjugate thing, if he's the acid, this is its conjugate base. Base. If he's the base, this is the acid. But the big thing is, hey, in this system, this chemical species is behaving as an acid. Now, if I just have bicarbonate ions in water, these things will remove a proton from the water to make this H2CO3. And if I pull a hydrogen off of that water molecule, what's left? Hydroxide. Well, geez, he's accepting the proton. Base is the you know what? In this reaction, this exact same species as above is acting like a base, and the water is behaving like an acid. So again, the Bronsted-Lowry definition accounts for that. It allows us to see that in some situations a chemical species might behave as a base. In a different situation it might behave as an acid. The conjugate relationship here, if this is the base, conjugate acid. This is the acid, the OH minus. The only difference between a conjugate pair base, the conjugate, the only difference is the difference of one lousy proton. Between this guy and this guy, how do the two formulas differ? They differ by the presence of one lousy proton. Those are conjugate acid-base pairs. Okay, let's take a look at weak acids and weak bases. I have found in the past when people have trouble with this topic, with buffers and with acids, bases in general, it's because they don't recognize the difference between strong and weak. So again, your strong acids, you should just flat out learn them. These are your strong acids. And if you're an acid but you're not a strong acid, you're a weak acid. So what do we have here? A strong acid, essentially 100% ionized in solution. So if I take nitric acid, add it to water, I don't have any HNO3 in there. I've got H3O plus and NO3 minus. So every molecule of this I drop in the water ends up transferring a proton to the water, making hydronium ions. 100% ionization. Now, weak acids. Weak acids are only partially ionized. It's an equilibrium thing. So here's some weak acids for you. Hydrofluoric acid, HF. You put it in water. Yeah, it tries to transfer that proton to the water. Yeah, obviously you go from here to here. You've transferred a hydrogen ion to the water. But guess what? The reverse reaction can occur as well. This fluoride ion can remove a hydrogen ion from here and you go right back to where you started. It's an equilibrium process. So here, is there equilibrium? A little bit, but we're talking in this reaction, the equilibrium is monstrously favoring the forward. There's virtually no reverse in that strong acid ionization. These weak acids, truth be told, for all of these weak acids, the equilibrium actually lies pretty heavily towards the unionized. There's a little bit going this way. So typical weak acid, acetic acid, this is the active ingredient in vinegar. If I drop 100 molecules of this into water, it starts doing its equilibrium thing. At equilibrium, I put 100 of these in solution, probably 97 of them are going to be like this, unionized. Maybe 3% of them will have transferred their protons over. So it's a weak acid. Now, for weak acids, hey, because it's an equilibrium thing, we have equilibrium constants, Ka, the equilibrium constant for the weak acids. And these things vary all over the board. You're seeing here for hydrofluoric acid, 10 to the minus fourth. Nitrous acid, that's not nitric. Nitric is the strong one, HNO3. Nitrous acid is weak. Nitrous acid, 10 to the minus fourth. Acetic acid, minus fifth. Hydrocyanic acid, boy, that's really weak. 10 to the minus 10th. So, who's the strongest of these? Oh, HF. The larger the value of Ka, the larger of the value of K, the more the reaction lies to the right. None of them actually lie to the right. They all lie way to the left because they're all really small numbers. But if you had to compare them, if you had to compare this guy with this guy, who's stronger? Oh, HF by far. So in the weak world, you have some that are weaker, some that are stronger. The way I've always thought of it, guys, this gets confusing for people. Weaker, stronger, weak, strong. Think of it as football teams. You have the NFL. The NFL, these are your strong acids. These are the proteins. These guys are super, super strong. 100% ionization. So you got the NFL. These weak acids, these are high school teams. There's no comparison, really. I mean, the strong acids, that's like the NFL. The weak acids, these are high school teams. But within the high school teams, some are stronger than others. You know, this guy here, HF, that might be the best high school team in New York City. That's going to be a pretty good football team. This is maybe the high school team from Deming, New Mexico. You know, it's they might win an occasional game, but you know they're a lot weaker. So anyway, hope that helps. Now, weak bases. A base is something that accepts a proton. It picks up a proton. And for the weak bases, again, it's an equilibrium thing. So what are your weak bases? The most common weak bases are probably the amines. Hopefully you remember from organic chemistry, anytime you have nitrogen plugged into a carbon, it's called an amine. They're derivatives of ammonia, which in itself is a weak base. Ammonia is another weak base. Nitrogen likes to have 3 bonds to it, as you can see here. But what happens here is when you have 3 bonds to nitrogen, you also have a lone pair. That lone pair likes to reach out and rip a hydrogen off of something. So if it does that, if this guy reaches out and it removes that hydrogen, boom. Now your nitrogen has 4 bonds. As soon as nitrogen takes on 4 bonds, it becomes positively charged. So the amines are weak bases. And again, it's an equilibrium thing. And they have equilibrium constants, Kb, because it's a base that it's behaving as. Now, the other weak bases, this part's huge. This part confuses sometimes, but hey, if you're a weak acid, you've got a conjugate base, right? Oh, sorry. A weak acid, you've got a conjugate base. He's a weak base. If he's a weak acid, the conjugate is a weak base. Weak acid, this conjugate is a weak base. Weak acid, there's his conjugate. Behaves like a weak base. So you see here, oh, you know what? HF is a weak acid. Can donate a proton. F- is a weak base that can remove a proton from water. And same thing holds. The larger the value of Kb, the stronger the base. So between all of these, who's the strongest of these bases? 10 to the minus 5th is a much larger number than all these others. So your strongest of these weak bases would be your cyanide ion. So weak bases. Interesting relationship with weak acids and weak bases. Mathematical relationship is if you take Ka times Kb for a conjugate acid base pair, they have to multiply out to give you this constant. The other way of doing it, if you're talking pKa and pKb, pKa plus pKb have to add up to 14. So a quick example here would be, let's take a look at this guy, the HCN. HCN has this Ka value, 4.9, 10 to the minus 10th. So 4.9 minus 10. That's the Ka value of HCN. Well, what if I want to know the Kb of the conjugate base? What's that number going to be? Oh, you can solve this real easily. You got a number here. You got a number here, right? You do 1 times 10 to the negative 14th divided by 4.9, 10 to the negative 10th. I'm getting 2 times 10 to the negative 5th. So cyanide here has a Kb of, 2 times 10 to the negative 5th. So that relationship is very useful. If you happen to know the Ka for the acid, you can calculate Kb for its conjugate. Again, conjugate acid-base relationships. What's the difference between those two chemical species? The only difference between them is H+. So they're a conjugate acid-base pair. Alrighty, let's take a look at buffers. Buffers are great. Guys, the world would not work with buffers. Your body would not work with buffers. Buffers control the pH of a solution. So let's see. The next video I'll show you how to do all the calculations with buffers. For right now, let's just see if we can get the concepts down. For a solution to be a buffer solution, it has to have 2 species in solution, both at a reasonable concentration. One of those species is going to behave like a weak acid. The other is going to behave like a weak base. So, if you have a solution that contains HF and its conjugate base, F-, it's a buffer. If it contains nitrous acid, which is a weak acid, and his conjugate base, which would be a weak base, it's a buffer. Weak acid, weak base, it's a buffer. Hey, what if you had something that contains hydrochloric acid and chloride ion? Hey, that's a conjugate acid-base thing. Is that a buffer? Nope. He's not weak. Hydrochloric acid is a strong acid. Super strong acid. Chloride ions, technically, we could call it the conjugate base, but there ain't nothing basic about it. So, if you have a strong acid and its conjugate, that's not a buffer. I had nitric acid and nitrate. Nope, not a buffer. So for a buffer, it's got to be a weak acid and its conjugate base. That conjugate base, of course, acts as a base. So you got to be in that realm of weak acid, weak base to be a buffer. Another thing that's used to make a buffer, if you have an amine and his conjugate base, it's a buffer. So remember, the amine here is a weak base. Weak base. His conjugate is a weak acid. So if you put both of those in solution, you got a buffer. Now, making a buffer, you got to mix up a buffer. 2 approaches to doing that. Oh, by the way, you don't make a buffer just by adding one of these to solution. Like if I just added HF, you might think, oh, HF is a weak acid, so it's going to react with water. It's going to do the minus H3O plus, and you might think, wow, okay, I've got my weak acid, I've got my weak base. That's not a buffer. The equilibrium lies so heavily this way. Do you really have much F-? No, not really. You have an incredibly small amount of that. For a buffer, you want the amount of your weak acid and your weak base to be roughly the same, or they might be 2-3 times different, 4 times different, but here, you're going to have like 1,000 times more of this than you have of this. So for a buffer, you got to put both things in solution. You got to go out of your way to make sure that both things have a reasonable concentration. So, real common way to make a buffer, you start with your weak acid. You grab a bottle of HF, pour it into a beaker. Now you got to supply F-. You might grab a bottle of sodium fluoride, because sodium fluoride is a soluble salt. It dissociates the sodium ions and fluoride ions. So, if I add this to my solution, it gives me a fairly good concentration of my weak acid. I add this to the beaker. Now I got a fairly good concentration of my weak base. Weak acid, weak base. Hey, it's a buffer. You took some acetic acid and add sodium acetate. Sodium acetate's a nice white solid salt. Hey, again, it's water soluble, so you get the sodium ion and you get your acetate ion. Hey, I got my weak acid because I added acetic acid. I got my weak base because I added the salt. They're both in there at a fairly decent concentration. It's a buffer. For an amine, you might start with the hydrochloride. This is representing a salt of an amine. These ones are a little confusing if you haven't hung around chemicals most of your life. What this represents is CH3, NH3, and there's going to be a positive charge on that nitrogen. Negative charge on, hey, it's a salt. This is a salt. So an amine that's reacted with hydrochloric acid gives you a salt. Hey, this guy's a weak base, right? Weak base. Guess what? His conjugate is a weak acid. So you got, if you were to put into solution some methylamine, and then you also drop in some methylammonium chloride. That's what you would call this, methylammonium. This is methylammonium chloride. You have your weak base, your weak acid together. You got yourself a buffer. So that's one way to do it, is to just actively add both things separately. Another way of doing it, another way to prepare a buffer solution. You start with the solution of your weak acid or your weak base. Then you add a carefully measured amount of a strong acid or a strong base to get your buffer. And you might be going, wait a minute. You said you can't make a buffer with a strong acid. Back when we're looking at what makes up a buffer, and I said it's got to be two weak things, a weak acid and a weak base. Here's what's going on. Let's say I start with a beaker full of hydrofluoric acid. This is my beaker. So I got 1 mole of hydrofluoric acid. He's a nice weak acid. 1 mole of that, and I only add half a mole of sodium hydroxide. Well, this reaction takes place. HF, he's my weak acid, reacts with my sodium hydroxide. It's going to make NaF. Oh, hey, NaF is sodium ions, fluoride. Oh, you know what? Yeah. So what the sodium hydroxide is doing is it's turning some of the hydrofluoric acid into the conjugate base. If I have 1 mole of this, I add half a mole of this. Guess what? I just dumped half a mole of sodium hydroxide into my beaker, but my beaker contains no sodium hydroxide at all. Why? The sodium hydroxide reacted with the HF. And what's in the beaker? Half a mole of this stuff, half a mole of this stuff. That's a buffer solution. Let's say I start with 0.75 moles of acetic acid. And I add 1/4 of a mole of sodium hydroxide. Same thing. The sodium hydroxide is going to react with the acetic acid. So the part of acetic acid that's the acidic proton would be this guy, the H. So what you have here is your CH3. Sorry, sometimes I do CO2H, sometimes I go COOH. So that stuff reacts with your sodium hydroxide, and you're going to end up making sodium acetate and your water. Oh, hey, that sodium acetate is a source of that, right? So basically, adding 1/4 mole of sodium hydroxide, that's going to destroy 1/4 mole of this. So instead of having 0.75, now I've got half a mole of it. As it destroys this, it's turning this stuff into this stuff. It's a real chemical reaction. Let's say I started with 0.3 moles of methylamine. So I got 0.3 moles of methylamine. It's a weak base. The amines are weakly basic. I add 0.15 moles of hydrochloric acid. Oh, methylamine. React with the hydrochloric acid, the strong acid. What's this do? Oh, that proton gets transferred over here. So I end up making so that's going to be my methylammonium ion, and I'll have my chloride ion as my counter ion. So I got a pretty reasonable concentration of both the weak base and the weak acid. So for buffers, you got to have both the weak base, the weak acid. How are they going to be related, these two? Conjugates. So hopefully you're seeing that this guy and this guy are conjugates. They only differ in terms of one lousy little proton. The proton in this case came from the strong acid. So hopefully you're seeing this guy and this guy. They only differ in formula by the presence of one proton. So he's the weak acid. He's going to behave as the weak base. The next video, I'll show you how to do calculations involving the buffer systems, and you take care.